what I'm going to talk about, so I mean, of course, there are a lot of materials that I cannot cover in this 1 hour like talk. If you wanted to read more about things that I've written like with collaborators in the past few years, so there are a few references here that the talk will be mainly based on kind of like the review article that I wrote with Ling and Lexing a couple of years ago. There are some later developments, or I mean, kind of more an article focusing on more recent developments that is in the chapter of the book that Eric and Nagaro are preparing for the Springer, and also for more mathematical works in trying to understand the thermodynamic limit, or the macroscopic descriptions of the density functional theory for solids. You can refer to this review article that is written together with David Gantier and Christoph Ottner. And also, like a few years ago, Ling and I wrote a short book as a lecture notes for a mathematical introduction to the electronic structure theory. And it's a kind of short book. And if you are interested in getting into the field, or want your students to get into the field who is more mathematical oriented, I think it would be also a useful reference. Okay, so I think everyone in the room knows about this equation. So I guess that's the starting point of electronic structure under at least the non-relativistic and Born-Oppenheimer approximation. And also, we probably all know this famous quote by Paul Dirac saying that this is, of course, very useful, but it's also very challenging to solve numerically or analytically. And even after like many years, almost 100 years, it remains to be difficult. Essentially due to the curse of dimensionality. So because this is a very high dimensional problem, it lives in, n is the number of electrons, so that it lives in 3n dimensional space. And for conventional numerical methods, if you want to discretize such a function, it's running out of the memory first of all, and of course, you cannot afford the computational time that is associated with it. And also, let me mention that there are also additional difficulties actually, which prevents us to solve this effectively. For example, one difficulty, as you probably will see later part of this tutorial, is due to the antisymmetry of the function, because we're talking about fermions, so that is satisfied the Pauli exclusion principle. That gives a lot of difficulties, for example, when applying Monte Carlo methods to this type of problems, and which leads to the infamous sign problems in the field of QMC, which I guess will be the topic of tomorrow. And also from a more like a numerical analysis point of view, that one also need to notice that these potential terms, for example, here, if you have like a nuclide, there will be something like a Coulomb interaction, and then there is this Coulomb repulsion with between the electrons. All these terms gives you cusp in the wave function, and so that the wave function psi has a complicated singularity structure, which also prevents some of the methods to be effectively applied for this particular setting. And as Kiron has already given a very nice overview, over the many 100 years, there have been many attempts trying to effectively solve these equations numerically. So starting from like very crude approximations using tight binding ideas, and then to the DFT, which I will talk more about. And then there were, of course, a very huge literature on the wave function methods. Some of them have been already mentioned. There have been recent developments by trying to use neural network to parameterize these wave functions as well. And then the Green's function methods, as we will see later in the tutorial, and also QMC. There were previous year, there was a program at IPAM about tensor methods, and these things have been also quite successfully used for some of the electronic structure problems, especially in 1D. And there are many more other things that we will not be able to cover. And among which I think Kiron has already given you the reason that why we want to focus on the DFT, at least for the first day. Okay, and it's been quite a successful story and being widely used for many. We have already seen the example even in coffee, right? So if you want to, just have a coffee break, and even coffee can be DFT can be even applied to making better coffees. Okay, so what is DFT? Give a slightly different perspective from what Kiron has introduced it about. Of course, it was pioneered by Hohenberg and Cohen and Sham in these two pioneering papers. And the basic idea, if you haven't seen it before, is essentially a dimension reduction. So instead of looking at the original wave function that we want to solve for the ground state from the many-body Schrodinger equation, instead we're looking at the one-body electron density, which is a function that lives on R3. Okay, so it's much of a dimension reduction from the original 3n dimension to 3 dimension. And the density is defined just as kind of like a marginal probability distribution of finding one electron at a position. Okay, so the n is a normalizing factor so that the integral of rho gives you a number of electrons. All right, and now, of course, one can think of this from the Hohenberg-Kohn theorem type point of view, but I think often from a more mathematical perspective, it's kind of easier to think in terms of the constraint search or the Lévy variational principle. So basically the idea is that, because we know, because psi corresponds to the ground state of the Hamiltonian operator, so you can think of the ground state energy as the infimum of the quadratic form of the expectation of the energy with taking the infimum with respect to all the normalized size. Okay, and the constraint search point of view is to think of this minimization into two steps. So the first is that you fix I fix the electron density, okay, and think about all wave functions that give rise to this electron density, and what are the minimum of the energy among all these wave functions. Okay, I hidden on rug some about regularity, but these are actually not so difficult to figure out what the regularity class of these functions are. Okay, and now suppose that you can solve this, and you name this as functional as some functional in terms of the density. Okay, and so if we know that, then we can only search over the possible one-body densities to find the ground state energy. So that's kind of the idea behind the DFT, or why it's in principle possible to come up with exact functional that if we can minimize it, then we'll get the ground state energy. Okay, and also ground state density, which is also part of this argument. Okay, and of course, this does not give you really what the explicit construction of the energy functional should be. And then, as you have already seen in the previous talk, over the years, there have been many, many attempts on trying to give you better and better approximations and climbing up the Jacob's ladder. And now the most, typically the kind of the energy form of these functionals come with such a form, which is also kind of natural if you compare with the original Schrodinger operator. So the first term here captures the kinetic energy associated with the non-interacting electrons associated with the density, and then the interaction with the external potential, the Coulomb repulsion, but replaced by some like a more classical type of mean field approximation. So I'm thinking of rho as a density. So this is the classical Coulomb repulsion between two clouds of electrons. And then you're making kind of like errors in these approximations. And then these difference between these terms with the original energy is captured by the exchange correlation energy. Okay, and which to some extent encodes, which is the most important thing to some extent, which because it encodes the many-body interactions between the electrons. All these other terms are kind of non-interacting or classical interactions between classical Coulomb interactions. Okay, and now more specifically, you can write down this kinetic energy for non-interacting electrons using the Slater determinants, because it's non-interacting. So written in using the Slater determinants, so that you come up with these like single particle orbitals, which these I label as psi i's, and they are in the regularity class of H1, so that the kinetic energy is finite. And the Coulomb-Sham energy functional, okay, which is the most widely used. I think it's fair to say that it's the most widely used electron structure theory nowadays. So that it consists of the kinetic energy of these orbitals and the three other terms that I mentioned before, and the link between the electron density and these one particle orbitals are given by the summation of the modulus square of these one body orbitals. Okay, and also for simplicity of notation and also the material, so that I'm only going to focus on the so-called spinless electrons, so that I neglect all the spin degeneracies and also all the sigmas. And apologize that if you're working on like magnetic materials or things like that. And also one thing to emphasize is that even though that mathematically speaking, I mean, this functional is written in the terms of using size as the variables, right? So that you see that you input size, you get rho, and then you can evaluate energy. But I mean, by the same kind of point of view of the constraint search, you can also think of this as a functional of rho implicitly, right? So you can think of a way as that you fix the rho as the input, and your size determined by minimizing the kinetic energy. And that's also one way to think about the Kumshan energy functional. Okay, so that even though in a certain sense, I replace the input from the one-body electron density to these one-body orbitals, it's still a density functional theory. I mean, so that density is the fundamental variable. All right, any questions so far? I mean, these are essentially just a very quick review of what Kieran told you already. And now for the exchange correlation, I mean, you have seen all these kinds of exchange correlation functionals. And so, I mean, I would just try to distinguish them into two classes, which is sort of relevant for, I mean, if you want to think about numerical methods. So the first class is that these functionals are semi-local in a sense that they can be written as the integral of some local quantities. Okay, so for example, in the LDA, they are integral of some function, okay, which only evaluated on the local density at the position x, and then integrate over a domain. Okay, that gives you total exchange correlation energy. And for GGA, the generalized gradient approximation, the local function not only depends on the electron density, but also depending on the gradient of electron scale in a way that, written in a way that it has the right physical scales. Okay. And so the other class, so these things are actually quite, I mean, so local, right? Because they're only depend, I mean, the whole thing can be think of some integral of some local quantities. While, I mean, there are also the non-local exchange correlation functionals. For example, I mean, just to give you, some examples here, so that, for example, it could be a non-local exact exchange, so that the exchange energy is written like this, so which is very much like the energy that you get from the Hartree-Fock theory. Okay, so that's also why it's sometimes it's called exact exchange. And then plus some RPA correlation, which I've written in this way, which is given by some linear response calculations of the and applying the random phase approximations. And I mean, if it's your first time to see these formulas, I mean, you may think that they are really, really complicated. But the only point that I want to point out here is that one thing you see is that they are, I mean, so probably the only thing that you need to remember is that they are non-local. Okay, so for example, this is given by a integral of things that depend on 2 points instead of the semi-local forms that the integrand only depends on the property of the variables at one single physical point. Okay, and then this thing is also quite complicated because it involves this operator, which is obviously not local. Okay, so that and also the new here is the Coulomb operator. So the RPA correlation is also fairly non-local. And now, I mean, in terms of, numerics, there are actually a lot of, issues that come up with, these non-local functionals. And I think yesterday, I think Lin was talking about some recent progress in calculation of solids. And some issues of how to treat these terms for solid systems when you truncate to a finite box, naturally appears, okay, because of the non-local nature of these terms. All right. So now, mathematically, right? So that if you think about this energy, and now what we want to do is that we want to find the ground state, so that we want to minimize this energy with respect to the inputs, the size. So the mathematically speaking, the thinking about this thing, if you have seen like other type of energy functionals comes from the calculus of variations from other different fields, it's actually kind of similar to many of the other functionals. Was there a question? No? Okay. So, even though that, you can say that it's actually true that Kumshan is not really a mean field type of approximation because, in principle, you can come up with very good exact exchange correlation functionals to capture the many-body interaction. But the structure-wise, once you fix the approximation of the exchange correlation, it is actually fairly similar, to some of these other variation, like Landau type of functionals that we often see. in the mathematical theory of calculus variation. And also in terms of the numerical methods, you can proceed along a similar way. So for example, I mean, so the approach is usually that you can differentiate functional with respect to the variable, which in this case, the size, the single orbital wave functions, and write down the Euler-Lagrange equation, or to say that, I mean, these the energy should be minimized so that it should be a stationary point, okay? Which is, I mean, the saying that it's Euler-Lagrange equation, just a fancy way of saying that. And then after, you need to do some trick to rotate the basis a little bit and to do some reductions. But afterwards, you can rewrite the stationary point equation into such a form. Okay, so into this form, which is usually the starting point of thinking about, I mean, the mathematical structure or the numerical methods for solving these Hongshan functionals. Okay, so the structure is the following. So you can think of that so the rho dependence in the into the functional, because it's a nonlinear functional, but it's actually encoded in some kind of effective Hamiltonian. So this Hamiltonian is a single particle Hamiltonian, as you can see written down here. So that is given by a single particle kinetic energy plus some effective potential. So it's a single. So I mean, the important thing that this is a single body. So this is a single particle effective potential. And the single particle effective potential, I mean, it consists of the external, I mean, I didn't write down the external potential here, but it depends on external potential, which is coming from the nuclei interaction, for example. And then the Coulomb part coming from the Coulomb repulsion, so that this term is actually just the Coulomb potential coming from the Coulomb repulsion between the electrons. Okay, and then some contribution from the exchange correlation functional when you differentiate with respect to rho.
I think there is a question.
Yeah, please.
So I have a question regarding the external potential. Is there any constraint like on linearity or having it bounded, or so we can continue in our calculation, or it can be any general external potential?
So I mean, first of all, I mean, let me make sure that I understand what you mean by linear. So it is linear in the sense that because it's external potential, so that it's acting on the rho as a linear term in the energy. So so when you differentiate with respect to psi or with respect to rho, you only get the V external. And other than that, it's pretty much can be just the model the reality, right? For example, whether it's some interactions from the nuclei or it's some external fields, or some electromagnetic fields acting on your system, or things like that. But of course, I mean, if you have some very like singular potentials, then in the numerics, one needs to be careful. But otherwise, I mean, it's just reflects the physics. Okay, good. Other questions? All right. So now you see that, I mean, once we have this effective single body Hamiltonian, the Euler-Lagrange equation or the stationary point equation for the functional tells us that we should solve the eigenvalue problem. And so the single particle size are the eigenvectors. Okay. And then the rho, I mean, corresponding to the sum of these modular square of these size. And I'm talking about the ground state or the zero temperature DFT. But as previously discussed, if you have like a warm matter, if you want to have finite temperature, then you need to, then you need to put in some occupation number here as well. Okay. And now one thing that I've already assumed that is hidden on the rug is that I have assumed the off-bound principle, which means that when so if you really go through the derivation and write down the Euler-Lagrange equation, the Euler-Lagrange equation actually only tells you that these size should be eigenfunctions of this effective Hamiltonian. But there was no proof, or actually the theorem is, there was no theorem saying that these eigenfunctions should be the low-lying ones. So from the first one to n, if you want to find the ground state of the Hongshan energy functional. And actually, there are counterexamples that this is not the case for some specific systems. But typically, at least usually in practical calculations, people often assume the so-called off-bound principle in the sense that the stationary points or the orbitals that we're looking for actually corresponds to the low-lying, the first n is the electron number, the first n eigenfunctions of this effective Hamiltonian. Okay, and now this is actually an eigenvalue problem. So that's why, I think on Thursday or Friday, and then we're talking about numerical analysis for some eigenvalue problems or non-linear eigenvalue problems. So that's actually why that is very closely related with solution of DFT. Okay, and there was another question, I think.
Yeah.
Please.
Yeah, so we solve this eigenvalue problem, and the first n eigenvalues we take, that will be, we sum them up, that will be the energy.
Oh, that's a very good question. Actually, it's not. So I don't have that in the slide, so I can not show you the formula. But the reason it's not is because thinking about there was nonlinear dependence here, right? For example, the Coulomb term. Okay, so let's just think about the Coulomb term. And if you sum over the first energy, the eigenvalues, sorry, not I shouldn't call them energy. Okay, they are sometimes called orbital energies. Okay, and now if you sum them up, right, so that this is, of course, just given by the inner product of the effective Hamiltonian with the inner product of psi. And the kinetic energy actually is correct. It's given by, I mean, so there is actually, of course, a term that corresponds to the kinetic energies associated with these orbitals. That's fine. But then the Coulomb term is actually already problematic, because if you sum them up, you will see that the Coulomb term, what you get will be this one. Again, I'm neglecting all the spin degree freedom, so that, I mean, there will be some constant of 2 or something like that otherwise. Okay. Yeah. So this term looks very similar to the actual Coulomb energy, but if we really compare, there should be a half there. Okay. And the reason is because when you differentiate, I mean, because this is actually a quadratic, it's a quadratic term depends on rho. So when you differentiate, you get a 2-factor from this quadratic term. Okay. And now when you sum them up, you mess it up, because, I mean, the V here, I mean, you're double counting, in other words. And the problem becomes even more problematic for the extrinsic correlation, because the nonlinearity there is much more complicated. So in fact, you really actually need to correct. So you can do the sum of the energy, but then you need to correct all these terms that, I mean, kind of double counted or like messed up from this nonlinearity, and then you can get the energy. Okay. But of course, you can also just, after you get these size, you plug in the energy functional, and that will give you the energy also. Okay. Other questions? All right. So now, one thing is that I want to already alluded to, I mean, which would be kind of important for later, is that, I mean, even though that, of course, it's kind of natural to think of this as a nonlinear eigenvalue problem, because that's the form of these equations are. But in a sense, since we're talking about the DFT, so that, I mean, the density is the fundamental variable, it's actually often easier to view it as a fixed point equation for the density rho. So what I mean is that, I mean, so think about this process, right? So you're fixing a rho here, you're putting the rho in the effective Hamiltonian. You get the effective Hamiltonian, and you're going through all this process of defining off-ball principle and finding the eigenvectors and sum them up, you get a rho. Right? And then what you hope is that, because it's not an eigenvalue problem, you hope that these rows agree. Okay. And this is actually, I mean, in mathematical terms, this is just trying to find a fixed point. Okay? And we can define all this process as a map, or Chebyshev map. So, I mean, this will appear also later in the slides, which maps the density, I mean, in this case, the single body density to another single body density, and you want to find the rho that is a fixed point of this equation. Okay, so this is kind of like another way of thinking about the structure of these equations, or what you want to solve for the Chebyshev function. Okay, yeah, so actually, I mean, I'm going a little bit forward in my slide, so that this is what I'm trying to say. So this is known as the Chebyshev map, okay? And you can define this through the eigenvalue problem associated with the effective Hamiltonian, or maybe a more intrinsic way of defining it without going through this diagonalization process, is that, I mean, given any effective Hamiltonian, what this map does is that it looks for the low-lying eigenspace, or in other words, you want to project out all the part of the spectrum of the Hamiltonian that corresponds to the part that's below the Fermi energy, okay? Or written another way, I mean, it's just the sum over the occupied space, or the first eigenfunctions. And I'm thinking of the projector into these eigenfunctions, so that this is also known as the density matrix in the physics literature, or, I mean, it's really the spectral projection into the low-lying spectrum of the Hamiltonian. And now once you have this density matrix, then we know that the diagonal of the density matrix, so density matrix is a two-body quantity. I mean, it's kind of a two-body quantity, right? Because it depends on both x and y, but the diagonal of it, which gives you the density. And I mean, assuming reasonable regularity for the potential, and these things are all well defined. Okay, so this is the Conjugate map. And now I will spend most of the time trying to give you some idea of the numerical methods and how people solve this. And then, some of these things are not just restricted to Conjugate, but also to other electronic structure methods that we'll maybe encounter during this week. So as we said, the task is really that we want to solve a fixed point problem, where this guy is nonlinear and also fairly complicated. Okay. And now, usually, to solve such a nonlinear fixed point problem, the usual idea in numerical analysis or in scientific computing is to do some iterative methods. Okay? And so, for example, the most straightforward thing or the immediate thing one can think of is that, okay, so because we want to find a fixed point, right? So how about just a fixed point iteration, meaning that I want to set my next iterate to be the output of my current iterate. And hopefully, the sequence would converge. Okay, hopefully this will converge to something. So, and you can see that if it converges, the thing that it converges to is better to be a fixed point of this map. And now, this alone, usually does not really work. In the sense that it may not converge. It usually diverges. But there are many kind of modern methods, or the more sophisticated methods, corresponding to this one, which is based on that we linearize this map. So this is a nonlinear map. So the idea is that we sort of linearize it and come up with a linear problem at the single time step. And then we use that to determine our next iterate, and which also could involve some kind of so-called mixing. So which, in the case of the simple mixing, it will be that instead of doing this, it will be that my next iterate would be some kind of linear combination of the output of this step. This is a really oversimplified version of the simple mixing. And then you do a linear combination of the output you get from the step with some with the input. And then you hopefully, you choose alpha to be something that's suitable so that this becomes a contraction map so that it converges to the fixed point. Okay. And so this is very typical, and it's in the field. It's usually called self-consistent field iteration methods. Okay, and the reason of its self-consistency is, is essentially the what I have mentioned here, right? You want kind of consistency between the input density to the effective Hamiltonian and output density that you get from the single particle orbitals. All right, and then of course, oh, there's a question, please.
So the alpha here is always constant, or we can have periodic coefficients here as well?
You can, yeah. I'm just talking about the most simple methods, and there are many more sophisticated ways to determine how to do linear combination of the previous iterate to minimize the residue, for example, or to minimize the energy. There are different ways to choose these parameters. Yeah, but what I'm trying to write down here is the most simple way of doing the so-called mixing. Thank you. Okay, other questions? Please.
So for doing mixing, do we have some properties of function mathematically that we know we use to our advantage to get these of mixing?
I didn't get the last part of the sentence. Could you please repeat again? So
do we know mathematically anything about this function so that we use that to our advantage in mixing and other stuff? Any regularity, anything about the function?
Okay, yeah, so I didn't get a full question, but if I understand correctly, the question was asking if there are any guarantees or any properties of the functional that we can use to prove the convergence of this iteration. Yeah, there are. But often case this is for very simple cases. For example, if you drop the exchange correlation And then for that system, you can see a lot about how these things behave. Or you assume for some very specific system, for example, you assume that your system is Galilean, which means that there is no external potential. And then with some simplifying assumptions, then you can analyze, because the convergence of this thing obviously depends on Jacobian of these iterations. In these scenarios, you can try to explicitly analyze the Jacobian, looking at spectral properties of the Jacobians, and then you can choose the alpha so that they will converge. But I would say, there was not really anything that is practically really useful for the realistic materials or for realistic functionals that people use in practice. But for simplifying problems, one can come up with theories and or convergence guarantees. Yeah, please.
Okay, thank you. Yeah.
Oh, sure. Yeah. All right. So of course, then this is after for every linear step, right? So that this is still a continuous problem. So we haven't we need to discretize them, choose a basis, and the choice of the basis set is another is kind of goes into a lot of works. And so actually in different fields, people typically using different choice of basis sets, like plane waves or chemical basis or atomic kind of like orbitals and things like that. And then there will be, the part which is sort of the dominating part of the cost is actually the evaluation of the Conjugate map after you, linearize the problem. So the structure is really that you have the electron density from the previous step. And as we know that the Conjugate map is defined through this effective Hamiltonian and the eigenvalue problem associated with it, so that we form an effective Hamiltonian from the density, and then we need to evaluate, to get the density from the effective Hamiltonian, which is usually the most computationally intensive step in this whole business. Okay. All right. Because so one reason is that if you think about this step, if you think about naively what to do, we go back to the eigenvalue problem, right? So that you need to solve the eigenvalue problem for the low-lying n eigenfunctions, and also the dimension of these Hamiltonians are typically kind of large, and solving a large-scale eigenvalue problems to get a bunch of low-lying eigenfunctions. This is the typically computational bottleneck. Okay. So now for the numerical methods, and especially for the modern numerical methods, one, kind of key observation to get rid of or to accelerate the calculation or to get rid of the huge diagonalization process is to realize that actually we do not really need these individual eigenfunctions and eigenvalues for evaluating the electron density. Because if you want to proceed, this iteration, right? As we have seen here, that the most important quantity that we need is really the output density, which is the sum of these eigenfunctions. Which so that for carry out these iterations, the individual eigenfunctions are not that important. Okay, so only so what's important is really just a representation of the low-lying eigenspace. Okay, so in particular, what we want is the density, but for some, I'm talking about semi-local functionals here, but for some more advanced functionals, we may also want occupied space. Okay, and so in the particular eigenfunctions, if once you want to realize that particular eigenfunctions are not important, maybe we should actually do a more intrinsic representation of the occupied space. And as we have seen before, right, so that for the semi-local ones, actually density is sufficient. So it's good enough if we can figure out what's the density corresponds to effective Hamiltonian that we have. And now on the orbital level, if we need, for example, exact exchange, we need this size, then it's actually also suffices to find a basis for the occupied space. We don't really need these eigenfunctions, so it's a linear combination of them is good enough. Or oftentimes it's useful to think about the density matrix, so which corresponds to the projection operator acting on these occupied space. Okay, and then this is just the Cauchy theorem saying that if it's an insulator or it has a gap, then the projection can be written down as a counter integral on the of the Green's functions. Okay, where the contour circles around the occupied spectrum. Okay, so these are the like the key ideas in a way for many of the modern numerical methods, so that we do not really need eigenfunctions. And now, I cannot really tell a whole list of numerical methods, so that I will give you some of these methods and talk about them, the ideas behind them. And but I try to list it here, some of these methods. So I mean, as we have seen that, I mean, one can think of these Conjugate problems as eigenvalue problems, so that of course one can do a apply a eigensolver like the traditional eigensolver, scale APAC or ALPA, and or but one could do also kind of more modern iterative based eigensolvers, and which I will kind of talk more about. I mean, there are like these things are really the standard eigensolvers. I mean, regardless of what kind of problems that you have. But I will talk a little bit more about the eigensolvers, particular eigensolvers for which uses the particular structure of the Conjugate problem, in the sense that we don't really need the particular eigenfunctions. It suffices to get the occupied space or the linear combination of eigenfunctions. And then there was a class called linear scaling methods. I'm listing a few of the like the well-known ones or the typical ones. And then I'll talk a little bit about the pole expansion and select inversion method. Okay, and I've been involved in this common library approach to solve the Conjugate map, which is under the name of LC. So if you're interested, you can look it up, which is like a common software package which implement many of these methods into a whole package. Okay, so now let me give you some idea of like the eigensolvers type of methods, but utilize the structure of the problem so that we do not really need a particular eigenfunction. So one of the methods, I mean, so is the Chebyshev filtering. And now, from now on, I will not write effective Hamiltonian. I will just write I'll drop the effective. I mean, just write the Hamiltonian. And the idea of the Chebyshev filtering approach is that, remember that we want the occupied space, so that we want the projection operator onto this low-lying eigenspace. And now what it does, I mean, so for the Chebyshev filter, is kind of an idea of the subspace situation where I use this X. So X is a collection of vectors. So it's tau skinny matrix. Okay, so it has n columns, which corresponds to the and this is the grid. Okay, so each column is a vector, is each one single orbital. And what it does is that it tries to filter out the high energy part corresponds to Hamiltonian. Okay, so that so this is why it's called Chebyshev, so that because it's actually a case degree Chebyshev polynomial that is applied to filter out the high spectrum. So if you think about the spectrum of the H, so this is the part you want, and this is the part that you do not want. So there are these eigenfunctions over there. And what you hope to do is to design a polynomial which looks like that. Okay, so that it's becomes small in the region that you do not want, but it's large in the region that you want to keep. So when applying these polynomials on these vectors, you're amplifying the part of these vectors lies in the occupied spectrum and filter out the unwanted ones, that is, which is of high energy. Okay, and now you see that this is actually quite different from traditional eigensolver, because you're not trying to like focusing on one of them, okay, and then doing some deflation and so on and so forth. You're really trying to focus on the whole occupied space.
Another question.
There was a question?
Yeah, so this Chebyshev polynomial filter is like a kind of, we can call it analog filter, right? So in computation, how that compared to some kind of digital filters that we can just put a hard cutoff there?
Yeah, the problem is that, if you want to put in a digital, if you're using your language, if you want to put in a digital filter like something like this, right, which is ideal, of course. But the problem is that, it's very hard to represent this as a function of H, right? So that this is a characteristic function acting on the H, and acting on the matrix. And to evaluate that exactly, you need to diagonalize the Hamiltonian first, right? So then you can apply in the filter of the singular, you can do a singular value thresholding or eigenvalue thresholding to filter out the unwanted ones, which defy the purpose because we want to get rid of diagonalization in the first place, right? And the advantage of this type of thing, which is soft, analog, but the advantage is that they're easy to evaluate because this is just a polynomial of H, right? So then you can apply, you do not need to diagonalize the Hamiltonian or diagonal matrix to apply the polynomial on top of it. For example, if it's just to, if it's something like H to the cube minus 2 times H squared, I mean, you can just apply this to the vector x, right? You can apply h twice and then apply h 3 times and then do it in the combination. So you don't, that's why you can avoid diagonalization. Yeah, this is a very good point. And also, I mean, one thing that, I mean, maybe should mention already also is that even though that we're not trying to find eigenvectors, but from time to time, we need to kind of orthogonalize them or finding some localized representation to avoid collapsing. Okay, otherwise, if we keep amplifying this and then everything will collapse to the lowest eigenstate, which is not what we want. Okay, and also there were better ways to accelerate this calculation. I mean, in more recent years, I mean, trying to do something a little bit better, closer to the Fermi energy. And so this is a pseudocode, and I think I can skip this, but I mean, the idea is what I've already explained. And now to talk a little bit about the linear scaling methods, or what they're about, or the reduced type of scaling methods. So the conventional approach of the diagonalization and even the Chebyshev accelerated methods, even though that this is much faster, but if you want to follow this approach, I mean, you need to apply this h to the matrices, and that cost is n cubed. And also the diagonalization of the orthogonalization cost is also n cubed, where n is the number of electrons. So the scaling of these methods is the same as if you just do a direct diagonalization of the Hamiltonian matrix that you get. Okay, and so that these these conventional methods, are cubic scaling, and I think in the previous talk by Kiran, we talk about the scaling relations between the different methods, like the couple clusters, and if you go up, then the scaling is even larger. Okay, so in comparison, of course, you can say that the Conjugate is actually cheaper because the scaling here is only cube. But if you want to go to very large systems, like it consists of tens of thousands or maybe hundreds of thousands of atoms, then you will hit this. This will give us a scaling wall. Okay, so that it still goes too fast. Because for example, if you double the system size, the computational cost goes like 8 times of the original system. And this also limits the scalability or the application of the Conjugate DFT to even larger systems. And now, if you want to reduce the scaling, and in a while there has been a very active line of research, which is called the order-n methods, or the especially for insulating systems or for metallic systems at high temperature. And the idea of these methods is based, the fundamental idea of these things, or why its linear scaling is possible, is due to the locality of the electronic structure. Okay, and the locality can be seen in many ways for these systems. And for example, if you're looking at the density matrix, it can be seen through that the density matrix will decay exponentially if you go away from the diagonal. So remember, the density matrix is a quantity that depends on 2 things. So that this says that this thing will scale as something e to the distance between the x and y once you scale away from the diagonal. And another characterization is that oftentimes you can find the localized basis for the occupied space. Okay, so sometimes called Vanilla functions. And so if you look at the eigenfunctions may not be localized; they may be spread over for the solid systems, or for molecular systems. Of course, molecular system, everything is decay. It's really a comparative kind of relative saying. So things are more localized, they're more spread out. Okay, and then the localization principle actually essentially tells us that it's possible to find very compact representation of the occupied space by looking through these localized orbitals. Happens here. Okay, and now using these things, there are many kind of approaches of how to do the so-called linear scaling methods. It's mentioned before that, for example, some method called local couple cluster, which is actually based on very similar ideas to reduce the cost, the numerical cost. And one method that maybe is one of the first methods in this category is the divide-and-conquer method by Wei-Tao Yang. The idea is that it's actually quite simple in a way that if you think about it, once you realize that it's possible. So the idea is just that if you give me a very large system, I start to partition the system into subdomains, and they could be overlapping. And I'm going to restrict the electron structure problem, or restrict the eigenvalue problem into these subdomains, solve them individually. and then piece them together to get the solution, get the electron structure or the electron density for the whole system. And you may think that this is a very kind of crude way, and it's like even too good to be true. But for some systems, in fact, you can rigorously justify that this would work. I mean, because of the properties of the locality of the electron structure. So in other words, the electron density in the local neighborhood will only depend on this local environment. So the impact from the regions far away would decay very fast. Okay, and again, I mean, this is also using the fact that we do not really need these eigenfunctions, because the eigenfunctions could be very delocalized, but impact, I mean, the sum of them, I mean, the impact in the electron density in the end could be pretty localized. Okay. And another kind of way, I mean, to kind of combining some of these ideas of eigensolvers and the linear scaling is that, I mean, sometimes, I mean, this is often kind of useful in thinking for many of these electron structure models, is that oftentimes you can come up with equivalent directional principles to solve, which could have some advantage in some specific settings. For example, I mean, if we're thinking about these eigenvalue problems, I mean, one of the natural way to formulate these eigenvalue problems is to think about the trace optimization, right? The trace minimization. So this is just a fancy way of writing, I want to minimize the sum over I from 1 to n of all these orbitals with effective Hamiltonian, and restrict it to the setting, the constraint that they have to be orthogonal with each other. Okay, so this is just the usual way of doing the eigenvalue problem, to think about eigenvalue problem as an optimization problem. Now, I mean, it's been realized, I mean, actually quite long ago, I mean, in 1993 by Maury, Galli, and Carr, that you can actually rephrase this into a alternative variational principle, which does not look like this from the first sight. Okay, but it turns out that it actually, I mean, it's the solution of this optimization is actually exactly the same as the previous one. And the advantage is that in this optimization principle, you do not have the orthogonal constraint. Okay, so previously, I mean, you have to make sure that all these vectors are orthogonal to each other and also normalized. But here, I mean, you can minimize over all possible x. Okay, assuming the h, I mean, you need to shift the h to make sure that h is negative definite, but that's not a constraint in practice. And then you just change, you insert in this term, which sort of motivated, as you can see, that if x is orthogonal, then this actually gives you the original energy. Wow, but I mean, this also penalized the x to be not orthonormal. Okay, and then you can also find occupied space using it this way. And the advantage is that now you can get rid of these, I mean, because we're not looking for eigenfunctions, so that you can look for better kind of representations of these orbitals. For example, you can look for these orbitals that are localized in space, okay, and you lead to a so-called linear scaling method. And I mean, this is just a side remark saying that, I mean, there is actually a active research line that, I mean, to find these localized orbital representations, and also known as the Vanilla functions. And there are like numerical methods and also theoretical work. And there are like, I think there are many people in the audience has contributed to this field. And especially I want to point out, I mean, the work by Kevin Stubbs, who is probably in the audience somewhere, who is now at postdoc at IPAM and who has worked on method called iterative projected position methods to find numerically find these Vanilla functions, or given a occupied space, finding these localized representations. Any questions for this? I didn't go into many details of these methods because I think this is really just to give you some flavor of some of these ideas, and without going into too much details. But I mean, if you find something interesting, you may feel free to ask, or I mean, or talk offline as well.
Hi, Jianfeng, can you hear me?
Yes.
Can you hear? So why use Chebyshev polynomials for the filtering of the high energy component and not some other orthogonal basis set?
I'm not sure. I mean, I get the question of orthogonal basis set. I mean, it's a polynomial, right? It's not a basis. So
well, I mean, they can be orthogonal, right? I mean, a set of polynomials can be.
Yeah. The good property for the Chebyshev is that you can try to like minimize for all the polynomials that you want to restrict as kind of a region that you want to minimize the amplitude, because this is what you want to suppress. Okay, and then the solution to that optimization problem will come out as the Chebyshev polynomial. So that's the reason that it's being used here. So the point is that you want to suppress the high energy spectrum as much as possible, and then it turns out that Chebyshev is the best choice for that.
Okay, so even better than just using an exponential, a decay function off the.
Oh no, I mean in the class of polynomials, of course. So yeah, if you can allow to use anything, then you can. I mean, this characteristic function or step function is the best. Because it was trade-off, right? You don't want to use very high degree polynomials. I mean, so what I should say is that if you want to fix the degree of polynomial and you want to suppress as much as possible, then the Chebyshev turns out to be optimal.
There's another question online.
So one quick question. So all the matrices that we are dealing with are sparse matrices, or they can be also dense? And are these like algorithm tailored for sparse matrices, or they're like general algorithms?
Yeah, that's a very good question. So so many of these, so it actually depends on what basis you use. So many of these ideas of the localized or the linear scaling method that I talk about here, which is based on the localization, certainly they highly depends on the choice of basis, and it's kind of need to assume that the bases are local, so that in other words, the Hamiltonian is kind of sparse, so localized around the diagonal, and then it's possible to kind of accelerate the computation if you have a local representation of the orbitals as well, because otherwise, I mean, first of all, if you choose a non-local like basis that like plane waves, I mean, okay, for plane waves, there were other ways to deal with that. You can transform to the Fourier domain, for example. But let's say you have a generic basis that is non-local, then these orbitals are not going to have a very localized sparse representation in this basis set because they spread out. And then these linear scaling or the computational saving using the sparsity will not be there.
I have a question about methods like Chebyshev filtering. So I guess they only make sense if if the exchange correlation functional doesn't require any of the non-occupied orbitals. Like, are there exchange correlation functionals that require these? Like,
yeah, that's a good point. That's a good question. So I mean, here, I mean, the Chebyshev part, I mean, this filtering or the structure of these problems, I kind of assume that it's a semi-local functional. If you have like a functional that involves all the excited orbitals, of course, this method will not work. And then it's much more challenging. And then, I mean, I think it's more like current research and how to design fast algorithm for these methods. For example, we can do 2-level iterations and things like that.
I do have a question about the orbital minimization methods. Like, how robust are they to finding the global minimum into choices of your initial choices of your orbit?
Yeah, so let me answer this in 2 ways. So first of all, I mean, in fact, it's proved in this paper by Kyle Thickey, who was a student graduate a couple of years ago, that if you look at this functional, if you look at the energy landscape, then there was no local minimum. So in the sense that if you start with any initial condition, and if you go downhill, and you're not stuck at a stationary point, which is unstable, so that you perturb a little bit, so that you always go down. And so because there was no local minima, so that all the point that you converge to is the global minimum. So in other words, you always find the right answer. But I mean, the caveat is that that's of course assuming that we're not doing anything fancy. So for example, if you want to apply this in the linear scaling context, what you need to do is that you need to truncate the orbitals, right? So that you cannot keep the full support of these orbitals. Otherwise, this is not linear scaling calculation. I mean, you need to say that outside this support, these orbitals are 0. And for that, I mean, once you truncate this functional, so you restrict, in other words, you restricted this x to a particular class, okay, or you restricted x here, then the behavior of these functionals could be very different. And in particular, I mean, you could easily create local minimum or false solutions, I mean, based on these truncations. And then, I mean, it's possible that you're stuck at some of these. I hope that answered the question. Other questions before I continue? Okay, and now the last idea that I want to maybe briefly mention about the linear scaling method, about these ideas of thinking actually better of different representation is that, I mean, so by the way, so this is a representation using orbitals, and the previous one is a representation using densities. So I'm just also giving you an example that sometimes it's advantage to change the perspective so that we can represent the quantity that I want to find using density matrix. Okay, and one kind of idea, using the density matrix-based algorithm is so-called density matrix purification. And what I write here is the famous Macquarie's purification. I mean, back in the 60s. So what the idea is that, I mean, you can just do iteration like, I mean, because this is a density matrix, right? And then the density matrix, just recall, is the sum of the projection onto these orbitals. And one property of this density matrix is that the eigenvalue is only 0 and 1, right? So the Macquarie's purification, the idea is that, I mean, it sets up a fixed point iteration such that once you reach a fixed point, the eigenvalue of this matrix has to be 0, 1. So it's in the end a density matrix. And then, I mean, this is like the behavior of this of the polynomial of the function here. And what it does is that if you start with a value that is above a half, then under this iteration, it will converge to 1. And if it's starting above half, then it will converge to 0. Okay. So now if you give me a Hamiltonian, I just need to, with a suitable scaling of initial condition, that is a scaled version of the Hamiltonian, then, I mean, I can guarantee that as this iteration goes on, I mean, the P will converge to the density matrix, okay, or the quantity that you're interested in. You can also see that this is a very different idea from the previous ideas that, I mean, this is utilizing the property of a density matrix, okay, and also from the onside, I mean, this is from the first side is has nothing to do with eigenvalue problems, right? But this also does a job, and now, I mean, based on combined with the fact that for some of the systems you can truncate the density matrix, I mean, they decay exponentially away from the diagonal, I mean, for locality, then you can also turn this into a linear scaling method of a fast scaling method. And this is known as the density matrix purification methods. And for example, the package NT-poly that being developed recently. And there are, I mean, I've just giving you the basic idea of the density matrix purification, but there are, of course, many different variations of these methods. Okay. All right. So now towards the last, let me briefly mention also the idea that of the PAXI, which is, again, I mean, a quite different utilization of the mathematical structure of these models to accelerate the computation. And this is based on the Green's function ideas or the resolving calculus of the density matrix. And this is a reduced scaling method. It's not linear scaling except for 1D systems, but I mean, for quasi 2D systems or for bulk 3D systems, I mean, assuming, I mean, so all these scales are assuming that Hamiltonian has to be sparse. Okay, so has the structure of the 2D structure of the sparse Laplacian or the 3D structure of the sparse Laplacian. Okay, and it's being incorporated into electronic structure packages. And the idea is actually based on the another representation of the density matrix of the occupied space, which is based on the integral representation or the contour representation. Okay, so what it does is that, I mean, remember that, I mean, so we have the density matrix. So let me, I'm skipping to the zero final temperature, but for the zero temperature, remember that we have this representation by the Cauchy theorem. Okay, where this contour, so in the zero temperature case, where the contour is contours through the occupied spectrum of the Hamiltonian, and I can just integrate over the contour of the occupied spectrum around the occupied spectrum, and integrate over, I mean, this the inverse matrix shifted Hamiltonian of the shifted Hamiltonian, then I'll get density matrix. Okay, so now, I mean, numerically, what one needs to do is just to kind of discretize this integral into a sum over poles. Okay, so I mean, you can do approximation using discretization, and then you get to have this formula. Okay, so you can represent the density matrix as an intercombination of the resolvents of the Green's functions as shifted poles. Okay. And I mean, this gives a picture of final temperature, and in final temperature, instead of you circle around the occupied spectrum. I mean, you circle around the whole spectrum, but then you need to avoid these other singularities of the Fermi-Dirac function at the inverse temperature, at pi over times the inverse temperature. Okay? And then you can design the shapes, or you can try to estimate these chemical potentials on the fly. You can design these poles and where put them. I mean, optimize them. There was some recent works in these directions. Okay, and then after that, you reduce the problem of finding the density matrix into sum over these inverse operators. Okay, but of course, I mean, if you just stop here, then you will see that from a scaling point of view, this does not seem to do anything, right? Because originally this involves diagonalization, so it's cubic scaling, but now you turn this problem into a bunch of inverse matrix, which is also cubic scaling. If you just naively invert a matrix, the observation is again that we do not really. I mean, for many problems, we only need the density or the region that around the density. So we only need the part that is near diagonal of this inverse operator, and for that, I mean, actually, we can accelerate computation. Okay, and I don't think I should explain this given how much time we have left. But just believe me that I mean we can accelerate computation by doing some trick from the linear algebra, sparse linear algebra, to accelerate computation and to only find the selected entries of the inverse matrix, and that achieves this reduced scaling that we claimed before. Okay. And so that this is the pseudocode for the operator, and as for the algorithm, and just showing you some scalability result of these of the method is highly parallelizable and can scale to thanks to the work by Ling and his group, and we can scale up to very large systems on the supercomputers. Okay, so let me trying to conclude and just give you some ideas of what's happening these days and also in the near future, maybe in this program. So, I mean, there are a lot of software development efforts, I mean, as I mentioned already, and also the LC and also the ELCL project in Europe by CCAM. And there are many, packages available for DFT and for large-scale computations, and they can be now routinely applied to larger and larger systems for practical applications. And now, this has been already discussed a bit during the talk, so that I mean, what I'm focusing on is really the semi-local things, and so some ideas that appeared in the last 20 years or last 10 years to accelerate the algorithms, to design fast algorithms for these semi-local functionals. And these days, I think there are many efforts in trying to accelerate computations for non-local things. So in particular, how to accelerate the, for example, the exact exchange functional calculations or some of these RPA calculations. And oftentimes the kind of observation is that one needs to rely on the rankedness of the representation of some of the quantities that's involved in these calculations. So, I mean, so in the linear scaling methods, we are kind of exploring sparsity or for the epoxy methods. And now for these dense operators, then I think one of the key observation or one key things that one needs to utilize is that even though these objects are dense, so that one cannot save the computational cost by using sparsity, but sometimes they could be low rank. Okay, so that one can reduce the cost by applying the whole matrix, for example, then instead of by applying the low rank factors. Okay. And then, I mean, of course, I mean, only talking about ground state things. I mean, there have been many exciting developments for excited states, time-dependent DFTs, or for strongly correlated systems. I mean, embedding methods, for example, I mean, these will be discussed further, I think, in later part of this tutorial. And also, I mean, I'm not talking really much about numerical analysis, but this is certainly important. And Benjamin Stam will talk more about that, I think, in his tutorial. And so, I mean, it's not only, doing numerical analysis to just guarantee that things will converge if you refine the mesh size, but I think most importantly is that how to make the implementation more robust and also hopefully make this implementation black box so that you can get guaranteed accuracy for some high throughput calculations, but not hand tuning things. And I mean, there are a lot of interest, I think will be discussed in this program about machine learning techniques for electronic structure, either to design functionals or to solve the electronic structure directly using neural networks, also so forth. So I think that's kind of exciting directions. And of course, I mean, there are a lot of efforts. I mean, because these problems are intrinsically quite difficult, the quantum mechanics problems. So maybe we should try to use quantum computers to solve them. So there have been also a lot of interest in developing quantum algorithms for these quantum chemistry problems. Okay, and I think my time is almost up. I would leave the last few minutes for questions. And as I mentioned before, these are references that if you want to read a little bit more about what I've talked about. Thank you.